Okay, so today I would like to present about something that I'll reveal later, but because like last time, because I think that good presentation comes from looking the part, but I don't have a cow suit, so I'm gonna use this instead. Anyways, the topic of the presentation is moving at expensive real-world functions, or formally using multi-objective optimization to solve expensive real-world functions. So here's the overview of today's presentation. I'll give you some background about the problem itself, and then the formulation for the optimization problem, and then we'll go into moving or optimizing with NSGA too. And then we'll move on to Bayesian optimization, and then we'll end with a discussion. So first, for the background, I'll start with K nearest neighbor search. This is kind of like the basis of this problem. Basically, given a point set P, which is a subset of real numbers in D dimension, and a query point Q, and a distance function delta, we want to find a set K such that the size of big K is exactly K, and everything in K is closer to the query point to everything outside of K. Does that make sense? In the real world, this problem is used to it's applied in information retrieval systems and recommendation systems, but finding exact big K is very expensive, so we usually just approximate it instead. There are multiple existing solutions right now. So there is naive linear search, which takes too long to compute, hash-based, which does not work in high dimensions, tree-based, which also does not work in high dimensions, and lastly is graph-based, which is where this problem kind of came from. The most graph-based algorithms have two phases. One is index construction, or building the graph itself, and the other part is searching the graph or searching the index. The algorithm that will be part of the project is called DISCAN. So DISCAN is a system that allows us to perform ANNS task, mostly for querying, but it also allows us to create the graph and everything along that line. And the algorithm behind index construction in DISCAN is called Vamana, and I might use them interchangeably because it's confusing when reading. Anyways, let's start with the first algorithm. This is not the thing that we're gonna be using for optimization, but this is one of the three algorithms that we will be optimizing the parameters for. So greedy search is quite simple. You start with a starting point S, and then you keep finding the closest. So P star is the closest point. Actually, let me start here. So we have the graph G, the starting point S, query point Q, and number of neighbors we want to look for, K, and the candidate set size, S. S is one of the parameters that we will be optimizing for, or use in optimization later on. But essentially, you start from the starting point S L is your candidate set, and then you basically just find points that are closest to the query point, and then kind of like look at its neighbor until you eventually get close, or like get closest to your query point. But the details of this algorithm is not that important. The important thing is that when you're doing the search, you keep a list of candidate points, so L, and L is you're upper bounding it with the parameter S, and that will affect the search time later on. And then the next one is called robust prune. Robust prune takes in a graph G, starting point P, candidate set V, distance scalar or distance threshold alpha, and a max degree M. Essentially, the idea is you start from the starting point somewhere. No, you're given a point, and then you kind of like expand its neighborhood, and then cut out the points that are close to each other. So the idea of nearest neighbor search is the marker. It's fine. I'll just hand wave it. So the idea is that you want your neighbors to be far apart from each other so that your search in the graph is diverse. So you have this threshold alpha to kind of control how close the points can be, like each point in your neighborhood can be to each other. And then there's the max degree m. So max degree m is just saying that each point in the graph can have a maximum degree of m, or maximum number of neighbors m. And then the last one is the main one, which is Vamana build. You initialize G as a random graph. You basically just connect the vertices randomly, and then you compute the medoid, or like the median in high dimension of the point set. And then you start from the starting point, and then you do greedy search to each of the points that you want to add into the graph. And then you will get like a set of visited nodes from the starting point to your new point, P. And then at some point you will like add more. Basically, it's like you add too many points into P's neighborhood, and then you cut it down so that it's down to size, and then you just use the algorithms that I showed before in order to do that. And from the three algorithms, we can see that there are 4 parameters. We have S, shown in greedy search, for the size of the candidate. C in Vamana build, C and M. So C and M is for the candidate size during search. So greedy, it's basically like the size of greedy search used in build. M is max degree, and alpha is in robust prune. These parameters affect construction time, search time, and search quality, which we will call recall from this point on, of the graph. So the obvious question is, how should we set them in order to make the performance of our graph the best? So next, we will formulate the optimization model. So the decision variables are the parameters that we saw before, and I applied these constraints because if the upper bound is too high, there is basically no point in keeping like a graph. You can just do linear search, and it will give you a better solution anyways. And the reason that we lower bound these two with 100 is because generally we want to find k nearest neighbor search where k is 100. So you kind of have to lower it, like the list of the candidate has to be at least as large as the number of neighbors you want to find. And alpha between this range is because of the algorithm, because of like the implementation that I use. And then the objective functions, we have 3 of them. So BP, I'm just gonna let it denote these variables as a vector. And then we have 3 functions where FC is time taken for construction, Fs is time taken for search, and Fr is recall, which is basically the quality of search result. And then the time taken for construction and search, we want to minimize it, and the recall, we want to maximize it. And then we will treat these objective functions as black boxes because we don't know what it actually looks like. So this is the full model. We want to minimize the construction time, the search time, and so 1 minus FR is essentially the error rate. So recall is in, like the value of recall is within 0 and 1. So this is basically computing the error rate. So we want to minimize the error, and then we have the same constraints. The next one is MOO-ing with NSGA. Encoding, so the way that I encoded this is because the upper bound is 1024. I basically represented it as a string of length 10, where it's basically a binary string. And then we do, for M, we just do normal conversion. For C and S, because it has a lower bound, it does the same conversion, but if it goes below 100, it defaults to 100 instead. And then for alpha, it just do this conversion. So X is the string, and then you convert it to the integer, and then divided by 1025 because alpha is supposed to be less than 2, strictly less than 2. So this will never be 1. And then like this number as a whole will always be in range between 1 and strictly less than 2. Does that make sense? Okay. So the crossover that I use, I have single concatenate, which is like the very basic one, and with uniform random selection, and also multiple concatenate with tournament selection and like other combinations of them. The reason that I didn't use permutation and stuff like that is because it's basically like binary strings where the permutation doesn't really matter. And then the next thing is a little bit about normalization. So we have let x star denote the Pareto front. The nadir and ideal point is intuitively, the nadir point is like the max value. So each component of the nadir point is the maximum value that the ith objective value can have. And then the ideal point is the minimum. In this project, there are like ways to estimate these points, but for this project, we will just use best found so far. And then the normalization is basically you take the point, take away the minimum, and then scale it into like the range, which is basically this. And then each objective value will be in range 0 and 1 for any of the objective value. And the first results that I want to show is for scaling and non-scaling. So for non-scaling, as you can see here, mainly the search time and build time, like the spread, is almost the same. So it kind of like goes this way. So it's like this direction. But if you're not scaling your objective values, the recall can dip below like the point where it's very close to 1. So that's one of the observations that I made. The next one is, so this plot is for every point that showed up in NSGA. So basically the entire population for every generation. And then, no, this one is. So this one looks a bit more similar, where the non-scale, the one that doesn't have scaling and the one that has scaling looks kind of similar, but this one is a little bit more spread out. And this is for each of the crossover and selection method. I would say that there is like this problem is not very sensitive to the method that you use for selection and crossover. And in order to kind of like quantify it, I use hypervolume, because I think the other methods, you kind of have to already know what the Pareto front is, because you have to like take distance and stuff like that. So I just take the hypervolume between these points, and then the other one is kind of where I expect the intersects at like the other extreme to be. And then these are the hypervolumes that we get. Essentially, most of them are pretty much the same, except for multiple concatenation. But because I only ran this once, like only one trial, because it takes too much time, I think this might just be like trial error. I will try to run a few more trials before I make any conclusions. So this one was without scaling, and then this one is for when we have scaling. So similarly, most of these are the same except for one, but I'm guessing that that's probably because of error of the trial. And this is the best solution. So this is the top 5 configurations with the highest hypervolume. Max degree is really high, and then it's really low, which I don't really understand. And the other thing is that we get a lot of duplicates in the final solution. And then these are the values. And then the actual objective values will come up later. And then if we do scaling, we get very different solutions. And the reason that I didn't put them side by side is because the hypervolume would be different as well. Yeah, and then this is the comparison of the objective values between the non-scaling and the scaling one. So this is the slide that I was making before. Basically, with direct comparison, scaling makes your build time go down. It makes your search time go down. Search time is, no, my eyes are killing me. Search time is also a lot better. This has 2 zeros, this has 3. And recall is mostly the same because the data set is not very large. So in general, we can see that non-scaling is worse than scaling. Sorry. It's okay, Ajahn. The rest is mostly plots anyway. So the next one is we're gonna fake MOO-ing with Bayesian optimization. So the main problem with NSGA is that it takes really long time. One trial with 10 population of 10 per generation and 10 generation. So basically, it's not that much. It takes 10 minutes just for one trial. And no, it takes about 2 minutes for each variant of crossover and selection. So in total, it sums up to about like 8 to 10 minutes depending on the run. So it takes way too long for that. So we can use Bayesian optimization. So for Bayesian optimization, we're going to use the weighted sum of the normalized objective values. One good thing with normalization is that because the objective values is now in range 0 and 1, this contribution without the weight will be equal. So you can basically control what you want to prioritize in the final objective value. And then just for simplicity, we'll denote this for the weight. And then weight 1 is for construction, weight 2 is for search, and weight 3 is for recall, or error. I didn't normalize it because it's already in range 0 and 1. So it will basically just like make the error bigger, pretty much. And the weights that I use in this is 1, 1, 1, where everything has equal priority. Recall priority is basically you want the most accurate result. Build and search time priority, now that I think about it, doesn't really make a lot of sense. The one that makes more sense would be search and accuracy. So it should be 1, 2, 2. I will try it out later. And then the last one is 1, 2, 3, which is that you want recall over search time over build time. And then this is the first set of plots for equal priority. We can see that the M is roughly between range 200 to 400, and then this one just kind of pop up out of nowhere. The next one is for C, same thing, about 400, and then there's like this point over here, probably about 960, which is the number that showed up earlier. And then for S, the best values are about 200 as well. And then the alpha is about 1.2. And then this is the top 10 configurations based on the weighted sum. The mean of the top 10 is for M is 247, about 250. This one is about 600. This one is for S is about 300. And then for alpha, it's about 1.15. And then the weighted sum is roughly this. But it's not very representative because it's a weighted sum. It's really hard to tell like how that weighted sum come from. The next one is The next one is for 112. For this one, we can see that M is around, the best M is around 600. Same goes for C, but for S, it's still down to less than 200, and then alpha is still around 1 to 1.2. And then this one is basically just numbers, so I'll just skip it. For this one, for build and search priority, M is really high, and C is really low. S is also very low. Alpha is probably the most spread out of all of them. And then this is the numbers. And then the last one is the different priorities. M is still about 200. C is still about 200 with some jumps to 900 something. S is around 200 as well, and alpha is ranging between 1 to 1.5. And then the numbers. And then if we take the top 10 of each weighting, and then we put it into one collection, this is what we get. And we can see that it's basically everywhere except for S, where it's around 100 to 250, and alpha is between 1 to 1.4, but the rest is very all over the place. And then this is the number where M, the mean M is around 400, C is 450, S is about 209, and alpha is about almost 1.2. And then here are a few observations. In the DISAN paper, the parameters used for a similar data set but bigger is that. And in another paper that compared different ANNS algorithms, the parameters that they use for DISAN is basically this. And for NSGA, we can see that the relative spread of build time and search time are pretty much the same, but recall can be worse without scaling. Compared to Bayesian optimization, the values is significantly closer to the parameters that comes from literature, but only if you have scaling, because if you recall, without scaling, the parameter for M at least goes up to like 960. I don't know why. And then scaling the objective functions generally gives a better result. And for Bayesian optimization, alpha is pretty much the only parameter whose value is relatively close to the value used in the comparison paper, and the rest is consistently inconsistent. But the thing is, from past experience running this and on my computer, I find that using higher values generally give better results. So maybe it's just a machine difference, because I run with a home desktop, and the researchers, they run on 1,000 CPU core supercomputer or something. And then that's it for my presentation.